Okay, hi everyone. Today we're going to solve another LeetCode problem that is 2421 number of good path, and it's a hard level problem and it has a very good like to dislike ratio. Although I will give you a disclaimer, it's a hard problem and it's a genuine hard problem. It is very fun to solve. It has like I think three important parts like sub problems, and if you are having difficulty in getting the intuition of this problem, then it's fine. I will walk you through the process, and let's see if we can understand this problem to the best and solve it. So in this problem there is a tree. So a tree is a connected undirected graph with no cycles, which means it's an n-ary tree and it's undirected, more importantly, consisting of n nodes numbered from 0 to n minus 1 and exactly n minus 1 edges. Okay, you are given a zero indexed integer array that is okay. So it's not an n-ary tree, I think, because it has n minus 1 edges. Yeah, so you have a zero indexed integer array that is vals of length n, where vals, so n means number of nodes, right? So we have number of nodes, and every node, every ith node has a value associated with it. So you are also given a 2D integer array that is edges, where you have an ai and bi, that is an undirected edge, that a is connected to ai is connected to bi. And okay, so a good path, that is this problem, number of good paths which we need to find. So what is a good path? A good path is a simple path that satisfies the following condition: the starting node and the ending node have the same value. Okay, all the nodes between the starting and the ending node have less than or equal to the starting node. That is, the starting node's value should be maximum value along the path. Return the number of distinct good paths. Okay, note that a path and it's okay, so we need to return the number maximum or the total number of distinct good path. And why it is distinct? Because we cannot overcount the duplicates, obviously. And the path and the reverse path is also not a deal. We cannot count them as twice. A path is a path, either it's counted from one node or the ending node, so from the start node or the ending node. So the reverse of it won't be counted as the same, would be counted as the same path. So for example, 0 to 1 is considered to be the same as 1 to 0, as single node is considered as a valid path. Okay, so in this question, so let's so this is the problem. Let's see how we can solve this problem. So a dry, like a thought process, and we will have a dry run. So a thought process is, if I can collectively collect all the nodes that have, so for example, this is a node, this is a node, this is a node, this is a node, and I only connect those nodes together. There was a path here as well, but I'm not taking into them consideration. Why I'm not taking into the consideration? Because they are greater than the, because this node value, that is vi and vj, and vi is, let's say, smaller than vj, right? Which means vj is greater. So for vi, the greater value will not exist typically, but for vj this value will exist, which means from undirected graph we are going to deal it in a form that is a directed graph. And after having this directed graph, then we will know that, okay, from this certain node, let's say from node a to node b, although this is an undirected path, right, undirected edge, but a value is, let's say, 5 and b value is 7, then 7 is interested in 5. 7 can flow to 5, but 5 cannot. Because if this A path is going in this direction, then this is not possible. Why? Because 5 cannot have a value that is greater than itself. And if the 7 is flowing in this direction, then it is possible, because 7 can have the values that are less than or equal to its own value, that is 7. So 5 is less than that, so we can have that. So this is one of the observation, and then we have values. Now what if I tell you that, why shouldn't we connect a graph in such a way? So first thing is, connect a graph connect the graph in such a way that all the nodes that are connected have meaning to their edges. So for example, in this way, so initially it was an undirected edge, but now this is a directed edge. And why it's a directed edge? Because this edge is never possible, although this edge is available, but it is never possible. And this edge from B to A is possible, right? So this is my main reason why we are going to change the graph a little bit from undirected to directed graph. Second thing is, we need to have these values. We need to use some, type of, let's say, creating some sets, creating some components of a graph, and using them in a way that it's more efficient. Because if we start this procedure, because the brute force approach for this problem, which I'm not discussing actually, I'm just skipping to the best approach. The brute force approach is kind of obvious. I think it's very obvious. All of you must have guessed it, that from each node we will try a DFS call and check if there's another node with the same value, and keep a track of it, right? From, for example, from 0, you will check if there's any other value that has the same value as 0, that is 1. Yes, there is one, so we will count it. And then we go to 3, there is no node that has, so from 3 there is a node that is, from one node 3 value, there is a node 4 that has the same value, that is 3, and there's another path, and from 2, and so on. Well, for every node we need to do a DFS traversal, and DFS traversal will take linear time, and for every node it will take order of n into n time. So that is order of n square, and n square will give you TLE. So this is like a brute force approach in a nutshell. And I think it's obvious, a lot of you must have guessed it, that why there's a brute force approach. Now back to the optimized one. Yeah. So this is the thing, like, right, we are connecting the graph, and yeah, now we need to connect the graph in such a way that it has directed edges, that every edge should have a meaning to it. A to B is meaningless. We cannot have an edge from A to B, right? Now, second thing is values. How we can use these values to our advantage so that the implementation could be much faster. Why shouldn't we? So first of all, I will say, why shouldn't we connect these edges? No, not connecting. I will say merge these edges, merge these, or create some components in these graphs in such a way that there is a node that is connected to them, right? And every other node that is connected to them has smaller value than the main node, than the parent node. And when these nodes are connected, and let's say there's another node that is connected to them and that has smaller values, now we can check if this value has a same value as the parent node, and this value has the same value as the parent node, then these nodes will contribute in making a path. And that path, right, and that path, so let's say they have same value, that is v and v, and there's a path between them which could have a lot of nodes. Now let's say that this path has some nodes, right? Because these are other nodes that are connected to the same parent, and there are other there are other nodes between them. But because we have changed the graph in such a way that we are only connecting nodes that are smaller than the parent node, these nodes values will automatically will be smaller than the current, smaller than these extreme nodes, the connecting nodes, and all of the nodes in the path will be smaller, which means now we can easily get how many number of nodes, how many edges, or the good paths that we have, which means we need to unionize the nodes with lesser or equal values. And the third part will be, we need to count how many same val nodes are there. And another thing that we are going to do is, so for example, there are 3 nodes, right? So let's say there is only one node. If there's only one node, then the path that we are looking for, the path that we are looking for is equal to, so the path that we are looking for comprises of at least 2 nodes. So if there's only one node, then it's 0, right? But if there are 2 nodes, then there's one path. If there are 3 nodes, so let's say there are these 3 nodes and there are nodes between them. Well, let's say how many paths could be there? How many paths could be there? So this is one path, this is another path, and this is the last path. So there will be 3 paths. Okay. Yes. And then we have 4 nodes. So when we are dealing with 4 nodes, how many paths can be there? So this is one path, this is another path, this is third, this is fourth, this is fifth, and this is sixth. So there are 6 paths, and so on with 5. You will see that there is a pattern, and this pattern is nothing but n into n minus 1 by 2. If you want to verify it by yourself, then you can. So 2 into 2 minus 1, that is 1 by 2 is equal to 1. 3 into 3 minus 1, that is 2 divided by 2. So 6 by 2 is going to be 3. 4 into 4 minus 1, that is 3, and that will be equal to 12. 12 divided by 12 divided by 2 is equal to 6. So this is the formula that we are going to use. Now we have everything in our control. So let's have a dry run. So this is the first dry run on the example 1. Let me get this example. Yes. Now we need to construct two things. So first is value to nodes actually. And then we have a graph. Okay. So let's start with the first value. That is value 1. That is 1. How many nodes are there that has the value 1? So 0 is there, and then we have 3. So I will say 0 comma 3. How many nodes are there that has the value 2? There is only one node, that is 2. How many nodes are there that has the value 3? 1 and 3. Sorry, 4 actually. How many nodes are there that has the value 4? There is no node, so we don't need to write it. Now graph, we need to change the graph as well. 0. 0. How many neighbors of zeros are there that has the value less than 0? Zero's value, and that is no one. There is no value because 1 has a value 3, 2 has a value 2. So nothing, none of these neighbors has a value that is smaller than 1. So it's an empty list. And then we have one node. So for 1, there is 0. So I will say 0. That has a value lesser than 1's value, that is 3. And for 2, let's see. 0 is 1, 0 is 1. Another is 3, and that's it. So 0 comma 3. Then you have 3. So for 3, you don't have anything that is smaller than 3's value. So an empty list again. Yes. And then you have 4. For 4, you don't have, yes, you do have 2, and you have 2 here. Fine. Now, I think by this structure, most of you may have realized that we are going to use a data structure that is also called union find. Isn't it? Union find data structure. Because we are, or disjoint union set, you can also say that. Disjoint set union. And you can also say that that's a name for the comparative programming thing. And this is a union find data structure. And we are going to basically create components, which I have talked earlier. We're going to create components of graphs, but that will be more like a set in this data structure. So let's see. Now we're going to merge them. How we are going to merge them? So for 1, because this is the smallest values, right? Because these are the values that we can have in our path. So I will say 1. Let's merge these values. So 0. 0's neighbor. There is no 0 neighbor. So 0 is staying as it is. Then you have 3. So 3 neighbor. There is no neighbor. So 3 is staying as it is. Okay. Now you will say that, okay, 0. What is the parent of 0? 0 is the parent of itself. Guys, listen, if you are having problem understanding this question because of the DSU or the union find data structure, then I will recommend you to have some knowledge of it. There are a lot of good documents available online, maybe some Hacker Earth tutorial or Geeks or Geeks, you can refer them. Or there are some videos available on YouTube as well. You can also watch them. So yeah, 0 parent is 0, right? Because in union find data structure, it's a very default tendency that every node will be a parent of itself until unless they have some other parent. And 3 is also a parent of itself. So 0 is a parent of itself, that is 0 parent is 1. So in this case, I will say 0 count. So count of the parent. We need to check how many nodes are there that have same parent, right? Because if there's only one node and 3 is also one node, then it means there is no path that comprises of at least two nodes, and there is no path that comprises of at least two nodes, which means their contribution will be nulled and it will give you 0. So you will not be adding anything into your answer. By the way, the answer will be initialized with the number of nodes. Why? So answer is initialized 5. And why it is so? Because it is given in this example that there are 5 good paths consisting of a single node. So single node is also considered as a path, but in our implementation, when we are finding the path, when we are finding the actual, the, I will say, right path, then I will say that we are looking for the path that comprises of at least two nodes, and there is no two nodes in the that have the value 1. We will go on further. Now let's jump to this part. On 2, I will say 2. Okay, neighbors of 2 are 0 and 3. So now this will be changed to that 2, and this is 0 and this is 3. This is how they are connected now. And yes, so from this point I will say at 2, how many parents are there? So at 2, okay, 2 is the only one that is a parent of itself, so 1 is again there, and this will be 0 as well, because we are requiring a path that has at least two nodes in it, and there is no node that has at least two nodes, right? And if you are still confused, then I will say you have to, and you are connecting, let's say from 2 you are connecting some nodes that has a value. So for example, 2 value is 2, but there is no node that has a value 2 again, because 0 value is 1, 3 value is 1. So there is no node that has the value 2, so therefore there will be no path, and that is why we have written 0 here. Now let's go to 3. At 3 we have 1. What are the neighbors of 1? We have neighbor 0. So I will say that 1 is now connected to 2, right? They are merged. And let's move to the another node, that is 4. And 4 is has a neighbor of 2, which means 4 will be connected to this, connected to 2 again. Now we are going to count how many same end, like a path which has a starting node and an ending node with same value. So let's start with 1. For 1, what is the parent of 1? That is 2. I will say that parent of 1 is 2, so 2 count is now increased to 1. And then we have 4. 4 and parent of 4 is also 2, which means 2 count is now increased to 2, which means that there are two nodes, x and y, that are connected to each other, right? And that means that there is actually one path. And by this formula we can also say that 2 into 2 minus 1 divided by 2, that is equal to, this 2 will be cancelled, and 1. So I will add 1 here, and this is equal to 6, right? This is how this answer is given. And let's okay, so let's start. Let's do another dry run as well. Okay, so at this for this value to node, for 1 we have 0, and then we have 1, and that's it. For 2 we have 2, and we have 3, and for 3 we have 4, and that's it. For graph, 0 is connected to 1, 1 is connected to 0, and 2 is connected to 3, and 3 is connected to 2, and 4 is connected to 2. Okay, so this is how the graph is, and the same process we are going to unionize them. So let's start with this value. For 1 we have 0. How many neighbors are there? So 0 has 1. Okay, and then to the next part, that is 1. 1 also has 1. So this is the same set that we are going to have. And at this point I will say, so how many, I will start with 0 again. So 0 has a parent, that is 0. So 0 count is, as a parent count, this is going to be in 1, and 1 also has a parent, that is 0. So this count is going to increment, and that is 2. For example, so now I will say that nodes that can contribute in a good path are 2. So if there are 2 nodes, then by the formula that 2 into 2 minus 1 by 2, we are going to have, by the way, the answer is initialized with the value of 5, because there are 0 to 4 nodes. And now we have one path, right? Because we have 2 nodes, so which means we have one path. And let's move to the other value set, that is 2. And now we have 2. So 2 is connected to 3. 2 is connected to 3. And then we have 3. 3 is connected to 2, the same set. And 2, the parent of 2 is 2. And parent of 3 is also 2. So this will be incremented. And now we have the same good path, the only one good path, because there are only 2 nodes. And now let's move to the another value set, that is 3. And 3 has a node, that is 4. So 4 is connected to 2. So if 4 is connected to 2, which means 4 is connected in this way, and 4 has a parent that is equal to 2. So 2 has a value 1, and 1 is not going to contribute anything. So yes, so 1 is not going to contribute in anything, and yes, 1 is not going to contribute in anything, so it's 0, and the answer is going to be 7, and that is your answer. I hope the question is now clear, and dry run of these two test cases is also clear, but if it is not, then you can comment below and I will try to help. I will try my best to help you. So now we need a union find data structure, right? And I will create that. So that is a class. I will create an object of it, union find. Some of the private data members are parent, vector, and rank. So we are going to do a rank compression. And then we have public access specifier. In this we have a constructor, that is union find. It's a parameterized constructor and has n, that is number of nodes. So first of all we're going to resize them. So parent dot resize n. Similarly for rank, and after that I will fill the parent with initializing every node as its own parent. So iota parent dot begin, and then parent dot end, and the starting value should be 0. And from there on these values will look like this, as 0, 1, 2, and so on up till n. So when this is done, then I will create a find parent function. This will give me the parent, and I'm also going to path compress it. So we're going to find the parent of x. So if parent of x is equal to x, then it means we have the absolute parent and we can just return that parent. Otherwise, if we don't have this condition satisfied, that parent of x is not equal to x, then it means we have an intermediate parent and we need to find the absolute one. So for that I will say, and path compress it as well, parent of x is equal to find parent of x. And after this I will say void merge. Now in merge there are, let's say, 2 nodes, that is x and y. First of all we need to get their parents. So I will say parent of x is equal to find parent of x, and parent of y is equal to find parent of y. So if parent of x is equal to parent of y, then it means they're already merged, right? We don't need to do anything, so we can just return it. But if they are not, then we need to merge them, and we will be merging them based on their rank. So if rank of parent of x is greater than the rank of parent of y, If this is the case, then parent of y is now going to be equal to parent of x, which means that parent of x has the higher rank, and now parent of y, all the set or the all the set elements that are into the that are connected with y are now connected with x. And else if rank of parent of y is greater than rank of parent of x, in that case parent of x should now be connected with parent of y. And else if there is a condition that they have same ranks, then by default I will say that parent of y will be connected with parent of x, and the rank of parent of x will now be incremented, right? So this is my merge, find, and constructor. I think we are done with our data structure. Now we can have the nodes. So int n is equal to vals dot size. Then we can have our union find data structure, that is uf. The object will be named as uf, and it has n, that is number of nodes. Yes. Now we need some other things, that is a graph. As discussed, the graph will be changed, and graph has a size of n. Then we also need some variables like int answer, that is equal to n initialized with n value, and then we will be adding the good paths that have nodes that have at least two nodes. And we need u and v in when we are constructing a graph, we need a source and a destination vector. And yeah, we will also be needing a map of int. We will also be needing a map of int and vector int that is equal to val nodes. And yes, I think that should be it. Now let's create a graph. So first thing first, we're going to create a graph. So for vector of int edge of these edges, so u is equal to edge of 0 and v is equal to edge of 1. Now if vals of u is smaller than vals of v, so if this is the case, or let's say smaller, not smaller but greater than, so let's say u has a value that is greater than v. This is very much like this. Yes. So so let's say u node is connected to v node, and u has a value 4 and v has a value 3. Now in this case I can make a directed edge u to v, right? Which means this will like graph of u dot pushback v. Now else if, not even else if, just like as it is, if but if the situation is changed that this is v and this is u, in that case this this edge, in that case the edge will be like this and v is connected to u, which means graph of v dot pushback u. Fine. Now when we are done with our graph, then we can create this structure, that is value to nodes. And this structure is you going to use this map of int vector int. And now I can start node is equal to 0, and node has a value less than equal, no, yeah, less than n, and node plus plus. And I will say that val nodes of vals node dot pushback node. Sorry. And then we can start iterating over these. So it's I think pair of int and vector int itr of val nodes. Now we will have two things. So first is a value, that is itr dot first, and another thing is the nodes, that is equal to itr dot second. Although value is not something that we need, so we are not going to have it, we are not going to use it, we are not going to initialize it because we don't need it. And then we are going to merge them. So the first step is to merge all the nodes that are small, that are in the neighbor list. So I will say int node of nodes, and then we have neighbors. Instead of neighbors, I will say adjacent node of graph of this node. And now I will say union find dot merge node and the adjacent node. When this is done, then we need a map, another map to keep a count of the same parents, right? Same parent, or let's say same value nodes count. That's a long name, but yeah, we're going to use it. And in this node, what we are going to do is in this part, what we are going to do is, yes, so there are nodes into this nodes array, and same well nodes count will keep track of these nodes. So I will say union find dot find parent of this node. So if there's a same parents, then it will be incremented again and again and again, and this is like insinuating a way that there are a lot of nodes, that there are these certain nodes that could be contributing in a path which comprises of at least two nodes. And yes, now we're going to calculate our answer, and for that I will say pair of int itr. We're going to iterate over this unordered map, same well nodes count, and in my answer variable I will say itr dot second multiplied by itr dot second minus 1 divided by 2, and then we are good to go and we can return our answer. Let's see if this will work. That's a whole like that's a lot of code. Yes, obviously typos. Let's solve them. So we have val nodes. We have declared it as val nodes rather than we'll say val node. Yeah, no, we need to use val nodes. Okay, the test cases are passed. Let's see if this will be submitted. Okay, it is. And it is performing very bad. Let's submit it again. Maybe there's some lag issue from the LeetCode server. Okay, again very bad. What could be the issue? Well, the time complexity will be n log n. And why is it so? Because we are using a map data structure for this part. So for this part, the time complexity will be n log n. And the graph part, when we are creating this graph, that is a linear time. And when we are merging these graphs, so this is also linear time. So, but the dominating term will be n log n, which is why the time complexity will be n log n. And space complexity, I think in space complexity we are not, we are using graph, which is n space, and value to nodes, which is an n space, and unified data structure, which is a yeah n space data structure. So I think the space complexity will be linear. And yes, I think that's it about the problem. I don't know why, because I think this is the, like, I haven't checked the solution section yet, but I am sure that this has to be a good algorithm, because, like, why not? But let's submit it again. Well, it is taking time for some reason. I don't know why. Maybe my rank compression is working. Path compression is also working. I don't know if this will make it faster, but let's see. Let's try everything that we can. No, no, obviously not. So if you have a better idea that is more, you know, taking less time than mine, then do comment below and I will make sure to check it out. So yeah, that's it. Maybe I should do some automatic structural binding. Okay, not so bad. But yeah, so this is the problem. And if you want to get the solution, if you want to check the solution section, that you can check it in the link of the solution is provided in the description. And if you want to check out the source code, it is also in the description. And if you want to try this problem by yourself, then the link of this problem is also given in the description. Thanks for watching, and have a good day.